So we're going to start this new section with a definition of a function, but this is going to be a definition of a function that's much more general than one that you remembered. A function f from set A to B, so this is defined in terms of sets. A function assigns each x in A to a single element that we call f. Sorry, I paused because I want to change this to a little a. So this changes to little a to a function from set A to B assigns each little a in big A to a single element f of A in B. Now, this isn't that crazy to think about or crazy to do. You should understand this quite well. If I have set A and set B, and this is a common sort of set diagram notation. If I have all of these little possible little a's in here, then my function assigns them to all these possible f of a's. What's going to be new here is we're not going to use the word range. We're going to use the word image. So it's called the image. Or sometimes it's called codomain. Okay, I can't write. Of little a under f. So, in other words, we're going to say that set A is the domain. And defining set A as the domain, that means that if it's well defined, then every possible element of A is going to have an image in B. Now, set B is not called is not the same as the image. This little kind of subset of B is what all the possible. This here represents all the possible f of A's. But set B is a larger set, and we call set B the target. And that is what classically is now known as the range. Now, since we expanded the definition of sets, what we kind of mean is that, in essence, we can have a larger range than we're actually using. We've seen this a few times, but we wanted to keep things simple in Algebra 1 and Algebra 2 by talking about domain range differently than we do in higher math. So sometimes your set A might just be all real numbers, and your set B might just be all real numbers, but your subset might not include all real numbers. For instance, f of x equals x squared. We're now going to call all the possible x's. Your domain would be all real numbers, but your codomain is the set of all real numbers y such that y is greater than or equal to 0. And your range is also all real numbers, because your range is the larger set of possibilities if we start expanding some things out. Or basically your range is what is the larger set that all your codomain elements are a part of. That's sort of how I think about it. So this is something just kind of keep in your mind. It's not a crazy complicated definition, but it's just something you want to know. Possibly another way to describe this, and this is a picture you see in your book pretty much, is that we have these elements of set A, that's the domain, and they're a part of some set that we refer to as the image. And all these elements in here, but that's part of a larger set called the target. And that includes elements that are not necessarily mapped to from the domain. And that domain, that's A, and this is B. So sometimes the image is the target, and that's another thing to keep in mind too, that the target doesn't necessarily have to be the image. And then this is called, that little arrow represents function f. So here's an example of how we can use proof in this, and there's a lot of different ways that this pops up. But this example just includes some of that terminology. We have a function defined from R to R. Now, what does that mean? Well, that means that we're going to input a real number and then output a real number. So this function is defined by f of x equals x over 1 plus x squared. And your task is to prove the image is the interval from -1/2 to 1/2 inclusive. I hope that all of you are very familiar with let's close that, with set notation versus interval notation, and that this represents -1/2 is less than or equal to x, which is less than or equal to 1/2. So just to kind of gather on that one. So if we want to prove that the image and the interval are the same sets, we have to pull on what we did before by saying that first the image is contained in the interval, which means that the image is a subset of the interval. And so to do that, we need to show that -1/2 is less than or equal to f of x, which is less than or equal to 1/2. If I want to do that, I need to first show that, well, the equivalent statement of this is I want to show that this is true, that the absolute value of f of x is less than or equal to 1/2. Now, if I want to show that, I want to show that the absolute value of x over 1 plus x squared is less than or equal to 1/2. Now, if I want to show that, then I have to show that this is true. The absolute value of x over 1 plus x squared is less than or equal to 1/2, because I can make this numerator just be its own absolute value, and the denominator is always positive. That should make sense. And if I cross multiply, really what I'm doing is I'm saying this part's true. And I can do that because I know that 1 plus x squared is positive. So essentially, this sort of show step is I'm working my way in reverse and saying this is what I want to show to be true. Well, I know that that's true because I know that, and I'm going to cycle back up here, I know that 2 times the absolute value of x is less than or equal to 1 plus x squared. And how do you know that? Well, if you were to actually subtract it over, you get 0 is less than or equal to 1 minus 2 absolute value of x plus x squared, or 1 minus the absolute value of x quantity squared. And if I start with this, and watch what this is going to happen here, if I actually start here and then work my way in reverse, I'm going to end up right back there. And that's an acceptable means of proof here. So since that is always true, then I've shown the image is contained in the interval because I've shown that this is true, that the image is contained in -1/2 to 1/2. Oops. So the next phase is to show that the interval is contained in the image. Which means that for y in -1/2 to 1/2, meaning for any value in -1/2 to 1/2, and I'm picking y because that's typically the one we use for an image or for a range, there exists, and that symbol means there exists in x a real number x such that f of x equals y. So what I'm trying to say is that for every number in -1/2 to 1/2, there's an x that some other number x, so that you can always assign that x to that y. So we can start by saying f of 0 is 0. That's kind of just a given plug-in, so I know that. So I want to look at now for y not equal to 0. And for y not equal to 0, and y in that interval, -1/2 to 1/2, we're going to set y equal to x over 1 plus x squared and solve for x. So if I do that, and I try to solve for x, I'm going to get y times, let's see, this is going to be y plus x squared y minus x squared equals 0, or written more quadratically, yx squared minus x plus y is equal to 0. This is now written as a quadratic, so I can use x equals opposite of -1 plus or minus the square root of 1 squared minus 4 times y all over 2y. And what we've done there, and you could simplify that a little bit just to make it cleaner. Sometimes proofs like that. Square root of 1 minus y squared over 2y. I've actually found an x that makes this true. Sorry, 4y squared. And I know that within this this quadratic formula solving right here, I know that 1 minus 4y squared has to be greater than or equal to 0, which means that y squared has to be greater than or equal to 1/4, or that the absolute value of y, there should be a less than or equal to, because the sign switch, and then the absolute value of y is less than or equal to 1/2, which implies that -1/2 is less than or equal to y is less than or equal to 1/2. So this is true. This means we have found an x, and I'll write that here. We have found an x for y not equal to 0 and y contained in -1/2 to 1/2. So we've accomplished it. We found part of set A, or part of the domain that makes this work. And the only reason it wouldn't work is if y was equal to 0, but we've already accounted for that right here. F of 0 is defined as 0. So for f of 0 equals 0, we've done it. And for any other y contained in -1/2 to 1/2, we can go right here and say, well, just use that. So we found it. And that means that the interval is contained in the image, which means that the image equals the interval. Believe it or not, we are actually stopping there because the homeworks are now going to get a little bit more tricky, and I want you to spend more quality time on it. So there's only 4 problems, but they're a little more challenging than the ones you've done already. 38, 45, 46, and then we go back and do 22. Bye-bye.